So, hello and welcome to the last session of the day. I'm delighted to introduce our next invited speaker, June Andronick, who will give a remote talk. Just to say that while CPP is at the end of our first day, June's day has started not long ago. In Sydney, it's 9:30 a.m. So feel free to ask her loads of questions. She can take them. June is well known in our community for her work jointly with Gary Klein and collaborators on verifying the seL4 microkernel with the proof assistant Isabel Hall, and more generally on developing methods and tools on the cutting edge of ever more comprehensive verification of systems in a merciless war against trusted code base. June played and continues to play one of the leading roles in the seL4 verification project and its extensions, including in her previous capacity as lead of the Trustworthy Systems Group at the University of New South Wales in Sydney, in parallel with being a principal research scientist at NICTA, at the NICTA, now Data 61. In addition to being CEO of the seL4 Foundation and conjoint professor in Sydney, currently June is CEO and co-founder of Proofcraft, where she continues her work on practical formal verification, seL4, of course, included. The Proofcraft company has the motto, "Software rules the world. Does it deserve our trust?" 11 years ago, when verified seL4 was listed among the 10 breakthrough technologies by the MIT Technology Review, June was also recognized by the same magazine as one of the world's top young innovators. I was a postdoc in the Isabel group in Munich at the time, and in the group where we were, of course, very excited by this recognition of a major system thoroughly verified with Isabel. But I always had one question that I never got to ask June, which I'm sure she has been asked before. What were the formulas on the whiteboard behind her in this picture, and how do they relate to the formal verification process? Today, June will look back at the seL4 verification journey, perhaps all the way back to the brainstorming session on that whiteboard. She will focus on the challenges of marrying formal proofs with industry demands. So, does industrial scale software deserve our trust, or does it have the potential to deserve our trust? June, you have the floor.
Thank you very much for the introduction. I'll just share my screen now. Here we go. So you should be able to see my slides now?
We can,
yes? Okay. So I can't see you anymore, but I'll go ahead. And yeah, so thank you very much for the introduction. Thank you very much for the invitation. It's really a pleasure to be presenting at CPP. And I'll try to answer some of these questions maybe towards the end. So yeah, my journey with the seL4 has been going on for quite a while, 13 years and a half. And it has given me a lot of opportunities to learn, opportunities to tackle challenges in all kind of challenges, as I had different roles along that journey. I started as a young researcher traveling to the other side of the planet to join that crazy project trying to formalize and verify an entire microkernel down to the C code. And yes, along the years, I ended up leading that incredible 60 people group, the Trustworthy System Group. And 6 months ago, I did a jump to create that company, Proofcraft, with Gary Klein and Rafał Kolański. So I'm a CEO of a 3-people company so far, including myself. And the company is there to provide commercial support for formal verification, including the support of the verification roadmap of seL4. So I thought that in this talk, I'll go a bit through those lesson learned when you start from an aim and a goal of the art and craft of proofs, and then how that meets the reality of commercial support. So just starting from the very beginning, the seL4 story really started as trying to tackle a mission impossible. And this was set up as a project that wanted to solve a problem that was both hard and world-changing. So that's how Gernot Heiser, the person that had the vision to start with, decided in 2004, I would like a microkernel that is formally verified. And being a systems person, wanting that microkernel to be usable, to be able to be taken by companies and embedded and so on, and therefore need to be performant. So good to have formal verification, but at no more than 10% performance degradation. So that was the aim. That's how the project of seL4 started, and the microkernel was created with formal verification in mind and high performance in mind as well, with the idea that the microkernel, being a operating system kernel, its aim is to then in a formal way provide isolation to applications running on top. So by controlling the accesses, it can provide isolation and then isolate critical part of your system from non-critical one, and therefore being protected against bugs or malicious attacks. And in this way, it can be world-changing by being able to protect systems that are embedded in safety or security critical system across a wide range of areas. So this was has been a dream, like verified operating system for decades, even when that was set up as a challenge, as the project we wanted to tackle. Of course, in principle, we would know that the properties of a program can be found out from the text by purely deductive reasoning, as was set up as decades ago by Tony Hall. And so really the challenge that had been tackled at the start of the seL4 story was to put it in practice for a real world microkernel. And this is what the team led by Goin Klein and that I joined midway through achieved in doing. So that was mainly the initial story, the initial breakthrough of the seL4 verification story. And so during this project, these 4 or 5 years, basically it was looking at the focusing really much on the proof themselves, the art and craft of doing a proof for a real world, complex, low level program that has high performance. And from then you can call it a success. And when you have success, you have new problems to deal with. And this is where you had different kind of challenges, which is deal with customers' demand that might got convinced that this is really a different solution that what exists, and want have requirement, have demands, have requests and features and so on. And this is, of course, an iterative process, because then you go back to your proofs because more proofs are required and so on and so forth. So this is what I want to talk about in this keynote, is mainly focusing on the lesson learned from dealing with customers' demand. I'll have a quick introduction on the seL4 proofs. That has been presented a lot of times in the previous year, so I'll just focus on maybe a different angle, which are the foundational techniques that have been used in the proofs, so that we have that as a background. But then I'll focus on 3 main components of dealing with customers' demands, which are their expectations when they start being interested in a seL4, then the fact that they usually want it all and want it now, and then finally at the end I'll touch a little bit on having to deal with making estimates of effort and cost to be able to have commercial contract with customers doing formal verification. So I'll start with the background and explaining a bit of the seL4 proofs by going through the foundational techniques that are used in these proofs. And that goes from refinement, forward simulation, Hoare triples, invariants, deep embedding, shallow embedding, using monads, some 2 properties, especially for non-inference, and translation validation. So this is a combination of all of the foundational techniques that have been used, with the breakthrough being to apply them and adapt them in a way that they're applicable, scalable, and being able to tackle low-level complex code. So starting from the start, what is seL4? It's this microkernel, so that layer that controls the accesses to the hardware, provides abstraction to components running on top. What it is concretely, it's binary code that can be embedded in the system. The code itself is compiled through a normal GCC compiler from the C code. And the C code is basically, in a simplified way, one function, a kernel call that the components on top can call. And then depending on the argument, then it will have all of the API that the kernel provides to the components, so the abstractions of the hardware and so on. So in the end, it's about 500 functions, roughly 10,000 lines of code. At least when it started, it has grown up now, but about to 15,000, I think. So the first thing to do formal verification is, of course, then to go into the formal world. And so in our case, that was Isabelle. So getting the C code, parse it using the C2 Isabelle parser into Isabelle Hall, and actually in a language embedded in Isabelle Hall that is mainly deeply embedded, that is called simple. And then you can start reasoning about that formalized C code. The way we've done the main first proof, which is proving that the code is correct with respect to a specification, is to define what that specification is. So that is an abstract functional spec. It's a state monad. It's defined as a state monad, which is a state transformer. So it takes the initial state and it produces the state after executing your function, as well as a result. It's actually a non-deterministic state monad, so it actually returns a state to deal with things like under specification, for instance. And actually, it has failures. So you also have a Boolean flag that can deal with undefined behaviors and things like that in C. So that's what the main first theorem of seL4 is. It's functional correctness, and it's showing that the C code refines the abstract specification. It's a standard definition of refinement with trace inclusion, but for all of the 500 functions that we have, it's proved by forward simulation, as it usually is done. But to do so, we had also to prove a number of invariants. And this is actually the biggest effort and the biggest size of proofs in the seL4 efforts in general, proving all of these invariants. So as you can imagine, a complex kernel would have a number of data structures, and all of this needs to satisfy and force an invariant that then is needed to prove that the code is correct. That's the main theorem number one. Main theorem number two is further proof on top of the specification, so security proofs on top. In particular, the kernel is there to control the accesses to the hardware and to memory and so on. And so the typical security properties are confidentiality, availability, and integrity. Availability is by construction in seL4, so mainly we have confidentiality and integrity. Integrity is the fact that if you don't have access, right, you cannot modify, so no unauthorized modification. According to the policy that has been defined for your system, meaning do you have the access right or not? And so what it says is that once you execute each kernel call, the difference between the initial state and the final state, all the modifications between those two are some that must be authorized by the policy. So it's defined as a predicate between the initial state and the final state with a given policy. And this is just defined as a Hoare triple on the abstract. So that's the whole advantage of having done the full functional correctness. You can do that proof at the abstract specification, and then you have the proof that is true about the semantic, the C code. So that's for main theorem number two, integrity. And then confidentiality is the dual, so no unauthorized reading or leakage, again, according to a policy. And this was done with a classical notion of non-inference, saying that you take two executions from two states, S and T, and if S and T only differs on on confidential data. Then when you execute the kernel and they reach states that still only differ from confidential data, it means that the execution doesn't depend on that confidential information, and therefore the information has been indeed kept confidential. So that's how we defined the confidentiality for seL4 at the abstract level, again, as a two property. Finally, we went further down, which is showing that the binary code is also correct. So it has the same semantic than the C code. This has been done not by proving the compiler, but by doing a translation validation, meaning that for each execution, the output of the compiler has the same semantic than the C code. So by first decompiling it to a formalized semantic, and then doing the match using a combination of Isabelle and SMT solver in this case. All right, so nothing is new here, just to get everyone on the same page and giving a bit of a flavor of which techniques, foundational techniques, have been used. So here you can have a summary of the deep embedding, the shallow embedding through the monads, and the type of properties that were proved at each level. The impact that means, once we've done that proof, is that the binary is correct with respect to the spec, and it enforces isolation. Isolation is the key word here. You know that it enforces isolation, which means that then you have the ability to host safely, securely, critical and non-critical application on the same system. And that's why it's the most comprehensive, and is still the most the system with the most comprehensive mathematical proofs. And thanks to the original goal from Gernot Heiser, it's also the fastest microkernel, which means that it can be used in real-world systems, and you can call it a success then. And when you have success, you have the good problems to have, which is that people want it now. And that leads to my part about dealing with customers' demands and so on. So I'll start with expectations. So it's interesting when you start discussing with people that have heard about seL4 and what they think formal verification might or might not be, and what it brings to them, and that, you know, it's not black magic in some way, something that you'll have to explain. But just trying to give a little bit of a flavor, some of the common patterns that we meet is that people are told in some way, in some setting, that they should really look into using seL4 for security reasons, for assurance reasons. Or they have done themselves some kind of market research, they're assessing their options, and seL4 is one of their options that they're considering. What they need to understand then, especially when comparing to other solutions, they want to understand what is it that the verification brings, what is the value of the verification. And they also want to understand what it means then for security or safety, but both are linked. So I'll focus on the security aspects in here. So these are the two things I want to dive into, the verified aspect and the security aspect on terms of expectations. This is, of course, when everything is actually the good. Sometimes they don't really want to know much about it. They just say, you know, like, can you just, you know, make it work and give us a tick that, you know, it's secure and we can claim it's secure and so on. And sometimes they're not even sure what security means for their system. And so we have a lot of discussions needs to happen in that sense. But I think the really important thing here is trying to convey to people that needs to compare solutions or need to bet on seL4 for good reasons, because their system might be mission critical or life critical or security critical. What does it bring? So usually when we try to explain verification, we focus on the fact that there is a mathematical proof. So that's the highest assurance that you can get about your software, because compared to other techniques, you can reason about all the possible behaviors rather than just some limited test scenarios or some process-oriented certification. And this is still very abstract most of the time. So even though that's still something that we keep pushing, it's still hard for them to use that to then convince their own customers or their manager or do their due diligence in terms of betting on this solution. So things that sometimes help are to be able to point to specific things like bugs that cannot occur once you've done formal verification. So in our slides, we usually have, in our technical slides, we usually talk about all the errors or undefined behavior that can't happen because of the verification, like the null pointer difference, overflows, injections, and so on. And of course, we keep saying, oh, but with doing full functional correctness, it's much stronger than that, because then you talk about all possible behaviors and so on. If you can manage to find examples of bugs that were found during verification and their impact if they would have not been found for the entire system, like for instance, isolation doesn't happen, information could be leaked, or you could have an entire kernel crash. This is also important. It's quite hard to get into, but we do, every time we touch a non-verified part, do find bugs every time we start verifying these parts. So if you can have these things help trying to put a little bit more concrete angle to just an abstract, the highest assurance possible. The other thing that I want to mention in terms of the value of verification is that, so if I come back to that, when they're trying to compare to other solutions, some of them don't have verification, so you would just try to focus on the value of any kind of formal verification. But then now there are multiple solutions that have formal verification, so you need to be able to compare and give means for them to compare them as well. So understand the various strengths and the various degrees of verification. So the way I try to explain it is taking those two dimensions that we can have. One is the strength of the properties, and the other one is the distance to reality. The strengths of the properties, you can try to explain that there are things that are on the verification side, more looking at specific lists of issues and vulnerabilities. And then at the other end of the spectrum, you had things like full functional correctness, where you can reason about all the possible behaviors. So you give an idea of strength here. And the second aspect is the distance to reality. So when we do formal verification, we have to take a model of the real system. And this model can be quite abstract or can be quite close to the real world. And that distance is an assumption. That distance is something that might still have issues or bugs. And so it's quite important to explain that the closer you are to reality, the stronger the verification that you're having has. If you can translate that into meaning for vulnerability that can be found with one or the other, it's quite good as well. So in terms of the distance to reality, when you're talking about software, it's quite easy to give the idea that you could reason about the spec only, and then about the C, and then you could go down to the binary. So this is quite easy to convey in the software world. And the other thing that needs to be understood is also, for multiple reasons in terms of expectation, is the scope of verification. And this is to talk again about the assumptions. And this is really important, so that for several reasons. One is that if suddenly you have sold a verified software and bugs are found, but bugs are in the assumptions or in the non-verified part, but you haven't stated them explicitly, then this can have a really damaging effect by, like the entire sector saying, see, formal verification doesn't work. So it's really important to explicitly state your assumptions and the scope of what is covered by verification. And I usually tend to say that the assumption is a good thing, because if you explicitly state them, this is, you know exactly what the scope of your verification is, and this is where you can then focus your attention on. So looking at those assumptions, because this is where the likelihood of having a bug remains, and you can forget about the other part which has been verified. And so the scope is really important for them to understand what is it that they're buying somehow. And this is in terms of assumption, but also in our case, the kernel is only a part of the system. And then you have all this rest of the software stack. So what does the verification of the kernel buys you in terms of the assurance of the entire software stack? And this comes the idea of the trusted computing base in software, and leads to my second part of talking about expectations, which is the security. The related link to security is also how much the isolation, in our case, help reduce verification. So I'll talk now about, after talking about the value of verification, about, in terms of expectation, how to explain the impact on security with the trusted computing base and the isolation. But stepping back just a little bit for security, let's look at the definition of what it means to be secure. So to be secure, if you take your favorite dictionary, which these days is probably Google, it says that it's protected against attack or other criminal activity. So one analogy that I took in the past was doing an analogy to martial art, because I practice martial arts, so that's really telling for me. In martial art, often people are, when they're receiving an attack, they're standing sideways. And this is because then you're minimizing the amount of body parts that an attack can come towards. And this means that the likelihood of an attack coming to the other part has been diminished, and you can concentrate your effort on just one side. This is the same idea when you minimize your code base and you minimize the attack surface just in terms of size. And this is true also about formal verification in some sense. When you apply very strong functional correctness proof to one part of your system, and you explicitly state the scope of what is covered, then you can concentrate your effort on the other parts. So it minimizes where you put your effort, but it also minimizes the attacks, in the sense that if attackers know that some parts is verified, they will likely put their attention in other parts. So in the first DARPA project that we had, HACMS, there was a red team, so professional hackers meant to try to assess and break into the systems, like the unmanned vehicles on which seL4 was embedded. And they would just say they would go for the weakest link. They would not even try to break what has been formally verified. They might look at the boundaries, the scope, so the initialization, the configuration, things that are in the assumptions, but then they will focus their attention to weaker parts of the system. And so having formal verification gives an idea that you minimize the attack surface, and then you can concentrate your attention elsewhere. So it's well understood for size of code, and this is something that you can use to say that this is also something that formal verification can bring. So starting from there, usually you have to explain the implication of having something formally verified in general for security. And the kind of questions you may get is, is having a formally verified software making it more secure? Well, that doesn't really make any sense. Like, more secure than what? If your system is intrinsically insecure in the first place, it won't get magically more secure by doing formal verification. If your system has security built in, then doing formal verification gives you an assurance that it has really extremely high probability to actually be secure. And then it tells you that you can focus the attention elsewhere, just in terms of likelihood. If the security is built in, you might still have tiny bugs or issues that can be found during verification. So yes, it can help you identify those issues and making it and fix them. You need to know what security you're looking for, but that's what formal verification can bring. So coming back to the initial picture about magic, it's formal verification is just describing reality. It looks at your system as it is. It will not change it or describe how you wish it was. It can help you to change it a little bit if you identify things that were not what you had in mind. But you need to know what you want in the first place. And so I think the main message that we try to convey when talking to people that want to use seL4 and what verification brings them in terms of security is security needs to be built in the first place, and verification will help you confirm that the security is enforced and potentially find and fix issues. Once you have done that, and if your security, in our case in seL4, is about isolation, then you can also leverage that in terms of formal verification. And that's the last part for security. So when we're talking to people about what is our approach to trustworthiness for software systems in general built on a kernel, the approach is like these 3 steps: componentize, enforce isolation, and minimize the TCB. So componentize is the idea that you don't want a monolithic software blurb that you put on top of the kernel. You want to componentize, because this way you can identify which parts are critical, because maybe they have access to encryption keys or things like that. And then these parts are the critical one, and the rest, like the orange in my slides, would not be as critical. So once you have componentized that, and hopefully you can minimize the amount of code that you need to trust, then if you can prove that you enforce isolation, which you can do with the kernel, then what you're doing effectively is that you're putting a box around the parts that is not critical, and that part does not need to be verified. So it's kind of obvious from a technical point of view, but that is something that you get from having done the verification at the kernel level about isolation, which then leverages, if you know what properties you want at your entire system level, then you can focus your attention to the TCB, which by definition is the part of the software that can compromise the security. So by definition, what is not in the TCB cannot compromise your security, and therefore doesn't need to be verified. So trying to summarize a little bit this larger part of my talk, which is about expectations, is trying to convey the value of verification and the strength of scope of what it means to be verified, so that people can compare the solution and really understand the value of betting for something that has been formally verified. And then what it brings in terms of security, once the security is built in, with the idea of a minimized attack surface, and the fact that isolation allows you to leave parts unverified in a secure way. So we reach a state where hopefully we have convinced people that it's that we have expectations matching, and we have convinced that it's formally verified software is something worth building a system on. And once they're convinced, that's we reach the I want it all and I want it now part of my talk. So if I go back to the proof stack that I've mentioned, or the proof structure that I mentioned for seL4, this was done in 2009. As I said, that was functional correctness. And then we have done the security proofs in 2012, 13, and then the binary proof. And in some way that was done, like in terms of demonstrating that it's possible, and that it's for performant microkernel success, it's done. But it was done for one specific hardware and configuration, so ARM 32-bit unicore. And so of course that might not be what people have, and being a microkernel, a lot of the code depend on which hardware you run on. And we joke about the fact that every new customer wants the entire spectrum of things, like, oh, we want multi-core RISC-V 64-bit with MCS, with FPU, with HYPE, with SMMU, with all the security proof done. And by the way, our next release in a few months. So I'll explain all of these acronyms as we go when they're needed. But the idea is that they want seL4 verified, but with X on Y. So what are the options that we have? Well, we have the architecture that it can be run on, so the platforms, so being ARM. So for seL4 would be ARM, RISC-V, and x86. The size, if you want, of the cone ice cream here, so 32-bit or 64-bit. Then you have the flavor of seL4. So in here, seL4 has seen a number of new features coming in. The biggest one is the support for mixed criticality system, which allow to reason about the amount of time a component has to execute, and therefore being able to enforce timing integrity and in terms of real-time systems. And therefore, we have two versions of seL4, one that is without MCS that I'll call vanilla, and the one with MCS. And one of them, the MCS version, is still being verified. And then you have extras, like do you want, virtualization extensions to be able to do to run as a hypervisor, things like that. And then, of course, you might be running in unicore or multi-core. So somehow, these are all the combinations of things that seL4, the code itself might exist for all of these combinations, but then for verification, we only have a selected combination that works. For instance, we would have it for ARM32 without MCS, we would have it for RISC-V, 64, and so on and so forth. And usually when the customer comes, of course, they want that combination that we don't have in stock, which is good and bad. It's good because then we can say, well, we can verify it for you and we can build a project for that. So the message here is there's no such thing as the seL4 proof anymore. Firstly, as I've said, there is different strength. There is the functional correctness proof, there is the binary verification proof, and there's security proof, just to simplify a bit. And for each of those different configuration, we might have only one of the proofs or all of the stack. All right. So there is this whole combination of proof that exists, and that brings a lot of challenges that we've talked about in previous talks, like scalability, maintainability, and also how do we tackle a new configuration when a customer comes and say, I want this specific combination that we don't currently have. How do we go about building it from what we've already done in the past? So the in some way, if you take your hat of the art and craft of proof, this is an amazing opportunity because, well, you could do abstraction, you could do parametric things, you can modularize. And we've done quite a bit of that, and that's a really interesting challenge. So, for example, not theoretically, in principle, the code that is architecture independent should be the same for all of these architectures. But then if you've done it only once for one architecture, you might not have split your proof in a way that you split what is architecture dependent and architecture independent. So since the original proof, this is something, for instance, that we've done. We've split for the following ones. We split the things that are specific to the architecture and things that are independent. And this has been quite effective, but it's for now only done for part of the proof. We keep developing that further for other proofs. Another example is the way the kernel, the way each architecture organizes and accesses their memory pages into page table is structured differently. And by having a more parametric structure, as we've done for the latest proof for RISC-V, has speed up the verification quite a lot. So these are just examples of things that we've talked about in previous talks. Other examples are, of course, how do you increase automation? How do you increase the robustness, the general robustness of the proofs? How do you apply proof engineering techniques so that doing that scalable and like doing those large scale proofs with all of this config in a way that is parametric and modular um, has created a lot of proof engineering challenges that we've tackled along the years. But the point I wanted to make here is then comes the second part is I want it now. So ideally, yes, you would do, like you would start, you would take the previous proof that you've done, you would generalize everything and so on. But if you are under time constraints, then comes the trade-off between generalization and just copy paste that and adapt, right? Of course, you have the obvious benefits of generalization having improvement that apply to all, and the proofs are more robust and so on. And copy pasta would accumulate technical debt that you have to deal with. You also have duplication, and when you have all these duplications and there is just like, let's say, a small optimization in the code, you have to duplicate that to all of the architectures in terms of the proof. So everything needs to be maintained. In practice, there's not an ideal world. Ideally, you take that into account during a project if there is some time. In practice, it often has to happen between projects, and that's even if you have time between projects. So not ideal, but basically, a lessons learned here. Finally, in the last part of my talk, I'd like to mention briefly estimates, because once you have the customer convinced that they will use a seL4 and you've discussed which configuration they want and when they want it and so on, then they would say, like how long and how much it's going to cost. And doing that for verification project, well, it's hard. Next question. Okay, so more seriously, what is the real challenge here is that there is an intrinsic risk that a proof is either done or not. And that's pretty hard to convey in an environment where people are probably more used to delivering code. So it's not like, I don't know, the code is not as optimized as you wanted or as maintainable as you wanted. It's like if the proof still has one sorry somewhere, like one proof that is still assumed, you can't say the proof is done. This might actually be completely wrong and have my repercussion beyond what you can think. So we've seen that in mathematical proofs in history. So, like no big difference in the software. You might have, like that tiny little thing you assume that is wrong. So there's an intrinsic risk that you have to go to the end, and that can, like, the end can shift quite significantly if you got it wrong. So it's really hard. There are some things that we've learned along the time that can help. Some of the things are the following. So trivial things, looking at how much the code changes, for instance, from one architecture to another, or from one version without a feature and with a feature and so on. If you happen to have done the spec already and are estimating the proofs, you can look as well as the differences within the spec. So when you look at the differences, you can look just at the size, but then you can look at the complexity of the change. And things that matter here are things like how many features or concept that it touches. So there are some areas or some objects or some functions that are quite standalone. And then there are some that are sprawling all of the main core of a seL4, like threads, for instance, that would be inside queues that have some bookkeeping mechanisms and so on. So the way it is spread out in all of the code really influences how much the effort is going to be. The second aspect is also how complex the change might be from past experience. For instance, some of the parts of the code we know are notoriously hard to get right. And therefore, we know that from the past, every time we looked at that one, the first time it's done for a new version, it has bugs. So if we know that there's some quite strong likelihood that this is not correct, or that the code is not mature enough and that we'll need a lot of iteration to get it right, and change the proof and maybe change the spec and then come back and so on. So that will increase the estimation. how much of the API changes, like if we actually instate a completely new function or call into the API. So these are just examples. What is also extremely helpful if we have actual data on similar project we've done in the past. It's rare because we often do something new, but the more, as a community, we have more and more projects in these areas, hopefully we can gather data on effort. And at least for seL4, we try to track how much effort things take and how much we diverge from what we originally estimate. And that helps getting estimates for future projects. That said, talking to the team and the engineers that what they do really to do those estimates, or people like Go and Klein that has all this experience, years of experience. Well, it's a lot of experience and gut feeling, a little bit like when a student asks you, how do I find a good invariant straight away? So anyway, that's about it. So yes, estimates are hard. It's really hard to convey that risk to the customers, but we do it. We try to know that there is a risk, and we try to find a way to put it in a commercial contract and take that into account. Sometimes we get it right. Sometimes we are a bit off. Sometimes we're a bit faster, which we're happy with, and so on. So that's the last lesson learned in terms of estimate I wanted to mention. So trying to sum up, trying to do art and craft of proof in a commercial setting where people have expectations and so on has a number of challenges. For expectations, the main ones are explaining the value of verification so that they can compare solutions, and also explaining the impact in terms of security, and then being able to deal with scalability, a number of configuration, being able to generalize, and that brings a lot of technical challenges, both in the research side of things and engineering side of things. And finally, like nothing technical, but just the estimates are really hard. And I hope as a community we'll get more and more projects that can give data on that and evolve that whole field forward. I'll just want to finish by saying, so yeah, it's challenging but doable. And the last thing I'd like to finish on is just a positive angle to that, is if people actually have expectations hearing about seL4, is that actually they know about it. And if they want it, it's a good thing that they want they want to bet on something that is formally verified because it brings some value. If they ask you for estimates, it means that they're willing to pay for it. And so interestingly, when you read, if you happen to read about what are the ingredients to build a successful business, these are some of the key ingredients. You have to have people know about your solution, want it, and be willing to pay for it. And that's why we believe there's some hope to build commercial support for formally verified software, and we created Proofcraft. But only time will tell. Thank you very much. I'm happy to take questions.
Thank you very much, June, for the inspiring talk. And yes, let's thank June. All right, so please post your questions in the chat. And also, if we have questions in Philly, please let me know, Stephen Leonard.
We've got one in Philly.
Okay, we can start with that one, and then we'll take one online. Please.
What sort of proofs have been done on top of seL4, or how would you connect kind of the soundness of seL4, the specification, to what it gives a customer developing something on top?
Yeah, great question. So I simplified a little bit the proof. So the main proof so far that we have on top is how do you initialize a system. So usually customers would have a system in terms of components that they have, the communications that they have between them. And so the idea is how do you then initialize your system in a way that your policy is enforced. And these, so we in our group have developed a tool chain for that, starting from a component platform where you can describe your components and connections, and then in a formalized way with the formal assurance being strengthened project after project, but basically being able to initialize your system in a way that you know that what you describe at your architecture, saying, let's say this component has access to this critical memory page, but this one has not, is actually the way that is enforced in reality. So that's the initialization part that ensures the componentization, if you want, and is a key component to the isolation. And this has been a key part of a number of the DARPA projects we've been in. So the HACMs to start with, but recently the CASE, the following one, the CASE project, with a number of partners that have been linking that tool chain to upper level tools like ADL, for instance, that are used in the industry to describe systems. So that's one thing, which is about how do you initialize your system. The obvious next one is, once you have identified your critical component, then you might want to do verification on there. And then there had been a number of projects in the group that have been going on, like at the language-based project, like Cogent. There is more recent project that are looking at that with KKML. So there are these three aspects. The one is ensuring isolation, which is what seL4 enforces, and then initializing in a way that you have those connections the way it will be enforced, the way you think it is going to be enforced, and then being able to verify what then is not encapsulated, what is still critical. Hope that answers the question.
We can take an online question now. Robert, so we have a question from Robert. Can we project it?
Yeah, I see the question.
So let me read it for the audience. You don't list the soundness of the proof assistant, including the correctness of its implementation, as an assumption on slide 30. Are commercial users worried about that?
So it is not in that slide, but actually, if you go on the seL4 website, there is a long list of, what does it mean? And actually, in 2009, this is when we started listing everything. What about this, and what about that, and what about that? So the assumption is listed in the long list of assumptions when we really go into detail. The way we phrase it, I think, is the likelihood is really, really, really low, like in terms of any issue being in the proof assistance compared to being in the other assumptions that we have. We do mention that we use the LCF approach for the proof assistance and so on. The soundness of the proof assistant is not generally a worry for most customers. If you go for an actual certification where people are going to look at which tool that you've used for the certification, they might look into that. I don't think it would matter if it's one of the... Actually, one thing that plays is how much the tool is used, like worldwide. Like if a bug was in the proof assistant, how likely would it have been found in the decade it has been used compared to, say, like a new thing that has been just popped up and so on. But so it really depends on the areas you're using it. Most ones are not worried about it. And as I said, most commercial users don't really understand the formal verification side of things. It's more if really you reach maybe the certifiers, for instance, and even there it depends how they know about those tools, how much they know about those tools.
Okay, and since we have the button online, we can take another online question, and then we can see if there's any other Philly question. So we have a question from Jesper Bengtsson, if we can project it. Another advantage of formally verified software is that you can make changes and optimizations and quickly see where the proofs break. Is this an advantage you try to push?
Yes, absolutely. So that's great. I had a small section in the previous version of my talk where I mentioned that, but then it became too long. So one of the really important things once we started to, in particular, have more contributions to seL4 was to have a really strong continuous integration infrastructure that combines the code and the proof. And one of the aspects is the one you mentioned. Every time there is a change on the code, how is the proof impacted? But also which version of the code, which version of the proof applies to which version of the code, and so on. So yes, it is something that is critical. In particular, so for the last 2 years, we created the seL4 Foundation, so an open source foundation. And this is now the entity that is managing seL4, which means that now we have more people that contribute to changes or suggest improvements, in particular optimizations. And if you want to make sure, well, first there is a very strong process in how to integrate those changes. If they don't touch any version that is verified, they can be integrated. If they touch version that is verified, they need to be verified first before we can integrate them. But either way, we need to know where the proof breaks whenever there's a change. So yes, we have now a complete continuous integration process. We have ways for people to check when they want to do a change, whether the proofs are affected or not, and where they are affected. So very good point. And yes, this is something that we do explain, and that the main thing, okay, if I'm fair, the main thing is, depending on the sector, some people are more interested in recertification. So let's say I've completely went through the other process, the process-oriented certification, and now I change something. I can tell you, yeah, okay, I can do the proofs and the proofs are done. What it means in terms of certification is another entire area of research or engineering that people want to get solutions, yeah, for.
Okay, thank you. Back to Philly. Other questions? Other
Yes.
local questions?
Yeah,
Yes,
we have one more question.
please.
Hi. Can you explain a bit more on the MPS thing, like you want to develop in the future? I hope I pronounced the acronym correctly.
So MCS is mixed criticality systems. So this already exists in the code. So it's a version that allows you. So seL4 is a capability-based system. So it means that every time the user level, the components want to access memory, they have to have a capability. So the access right in terms of memory is done through capability. The MCS version is using those capability to manage timing. And that means that a component has a given budget of time that is controlled by capability. And this allows to enforce timing protection in terms of integrity, meaning that a component cannot overrun its allocated time and therefore prevent another more critical component to run. So this is the version of mixed criticality of seL4. The code exists, it has existed for a while. The verification has proved very challenging. So that was one of the changes that was the most challenging, because it touches all of the like, it's a new mechanism, new kernel objects, new kernel calls, and so on. I hope that was your question.
Okay. So are there any other questions any other local questions?
Andrew, you have a question? Yeah.
What's the difference between the kind of verification work you do when you must publish papers from it and the kind you do where you don't need to publish papers from it?
Okay, I'm trying to think. So the main thing about publishing, so publishing paper needs to be, maybe I'll say things that offend people in both directions, so I'm not sure how to say it. but I think it's good in both directions. It both have benefits, but when you publish paper, you need really something that is novel, different, and that you're solving in a very different way, so that has a clear benefit in the way you solve it and so on. But then you might stop at the prototype and you've proven that it works once and that's it. Whereas in the one where you don't publish, you might want to make it in a way that really works in practice for all of the examples you have. So that's much more on the engineering side. That said, we had a lot of discussion about proof engineering, whether it is research or not, because there's a lot of things in there that are completely research. Like, how do you find engineering, like engineering as a research discipline? How do you find techniques that are like generalizing proofs? How do you have conditional inclusion of a proof in Isabelle? And you just include that part if you're in this architecture and include that part if you're in this other architecture. So these are completely engineering problems, but that has research challenges and that you can publish for. It's a hard question. Yeah.
All right, thank you. Since there are no more online questions, before looking back at for local question, let me insert a quick question which probably has a very simple answer. Is there any art or science behind arguing for verification, let's say for large systems, for verification as opposed to testing? Because testing has these beautiful words called complete coverage and so on. So does the argument go along the lines of this bug would be very difficult to catch by even comprehensive testing, or would it be too costly to actually test it so thoroughly, or what is the art of argument here?
I think there's a lot of this is hard. This is what I've tried to convey, and especially for bug finding, and especially for things where you have, like, you can't compare having it done with testing and having it done without testing, like it's like with verification. So you compare apples and oranges a little bit. But it is true that the complete coverage is never really a complete coverage. Like you have, like you can find those typical examples where you've been through all of the branches and yet you have that issue. And if you can translate that, I think the art is really to translate what it means in practice. Like, well, your secret is leaked, or you get a kernel crash and you have to reboot, and this takes 3 minutes, and you're in an aircraft that is, controlled by your software, things like that. So it's more making it concrete than anything else, so not very technical. But yeah, and I owe you an answer. That whiteboard has nothing to do. You have a photograph coming, and they say, we need to find a nice place. Just go there, and I'm like, but that whiteboard is not. It's like, that's fine. Just stand in front.
Those suggested formal proofs possibly for the
yes, there were formal proofs, but I think there was nothing for a seL4.
I see. Okay. Okay, there's another online question. If we can post the one from Jim. Yeah. Do you think less testing is done for verified software compared to unverified software?
This is an argument that so it should, as long as your scope, you should be able to do less testing, of course, as long as your scope of assumption is really clearly stated. And then you can actually do testing, much more testing on the parts that are not verified, or the boundaries, as I was saying, of the scope. So for instance, in our example, we assume things about caches or about TLBs and things like that. So the interesting point for this one is, how does that translate to certification? Because certification processes and schemes are quite conservative, and telling them, and they're costly because they go through, like this intensive testing and this intensive process, and trying to convince that, well, you have formally verified things, so you should be able to do less testing is more challenging. So that is still a hard thing, and especially for trying to convince people then the cost, like trying to convince that they should be able to do less testing and therefore reduce that cost, especially if they have all the infrastructure already to do that, whereas they don't have the infrastructure maybe to understand the proofs or maintain the proofs in some ways. Yeah.
Okay. We will need to conclude.
We have,
So unless there is a stringent question from Philly
we
remaining.
have one more question. Is it
Please.
a short one?
Yeah, go for it.
So my short question is, what about side channels? Do customers worry about it, and is there any low-hanging fruit as far as seL4 is concerned?
So yeah, so this is the main one of the main great challenges that the Trust of the System team remaining at UNSW is tackling. So a principled way to tackle timing channel. So I would refer you to the recent papers that are going on with on seL4. This is a battle that, so this is mainly led by Gernot Heiser at UNSW with his team that remains there, and one of his main battle is about the hardware-software contract, because you can solve it at the software level, but the hardware needs to provide the mechanism, which it doesn't at the moment. So there is some hope with RISC-V and being able to influence that. But yeah, so there's, yes, absolutely some research in terms of timing channel. Some of them are, so residual timing channel are considering the proofs that we have, confidentiality proof, but the actual timing channel, covered channels are something that they're currently publishing paper about. So you can look at those.
Excellent. So let's thank June again.
Thank you so much.